this lecture, we will solve a numerical problem about polar decomposition. Now, by a polar decomposition of the deformation gradient f for the shear deformation, this is R, the motion, see, motion. x1 and x2 correspond to the spatial coordinates. Capital X1, capital X2 correspond to material coordinate, see, related to the undeformed configuration. Now, you see x1 is 5 capital X1 E1 plus 5 x2 E2. x2 is equal minus x1 E1 plus 7 x2 E2. Determine the right and left, attention here, right and left extract tensor S and T together with the rotation tensor R. Now, you see, look, we want to obtain the polar decomposition, but before we write the single value decomposition in which F or any matrix A, okay, here we are using A is equal F is equal U sigma V transpose. Don't forget that U is related to the column space and V is related to the row space. As we did previously, I think the previous two lectures, we introduced single value decomposition. Now, let's calculate F, U, sigma, and V, or V transpose. It's the same thing. Now, immediately, we can obtain the matrix F, in which is the deformation gradient. You see, F is the deformation gradient. Define as partial derivative of xy with respect to capital Xj. This is a matrix F. These are the elements of F. Now it's quite easy. You see, x1, okay, partial derivative x1 with respect to capital X1. You see, this is 5 over here. Now, partial derivative x1 with respect to x2. So, x1, the partial derivative x1 with respect to x2 is 5. Now, the second row, partial derivative of x2 with respect to x1, so this is minus 1, is over here. And partial derivative of x2 with respect to capital X2, which is 7. Now, we obtained the matrix F, the deformation gradient. This is a tensor, second order tensor, see Ij. Now, to calculate, look at here, we want to find F, already did, U, sigma, and V transpose. Now, let's eliminate U, okay, doing the product F transpose times F. This must be a symmetric matrix. You see, U sigma V transpose, you see, U sigma V transpose times F. You see, this is F transpose, this is F. Now, as we did before, the transpose, this will come first here, this will be V, sigma transpose, U transpose. U transpose times U is I, so G is equal V, sigma transpose sigma, V transpose. But we can obtain G. G is F transpose, you see this F transpose times F. If you multiply, we obtain 2618 for the first row, 1874 for the second row, and observe that this matrix is symmetric. We can observe that, you see, this matrix here is a diagonal matrix, is the eigenvalues, attention, the eigenvalues of G. You see, F transpose F. And V is the eigenvector, the columns of V are the eigenvectors of this matrix G. You see, we can calculate. Just obtain the eigenvalues. You see, now the next step will be the eigenvalues are and eigenvectors of G with equal F transpose F. You see? Now let's calculate the eigenvalues and eigenvectors. Now, if you have some difficulties, please go to examples that we did in many lectures, okay? Solving eigenvalues and eigenvectors of a given matrix. So let's calculate the eigenvalues and the eigenvectors. So the determinant G minus lambda I must be 0. So the determinant of 26 minus lambda, 18 and 74 minus lambda, this is equal 0. So this implies, this is lambda squared minus 100 lambda plus 1600. This is equal 0. This is equal 0. You see, this here we can write in terms of these products. Lambda minus 20 and lambda minus 80. Now, let's obtain the eigenvectors for lambda is equal 20. You see? Now, how we get eigenvector? Let's put an S over here. Eigenvector for lambda is equal 20. So this is a matrix. You see? Now, G, the matrix G minus 20I times X is equal 0. Now let's G minus 20, this will be, see, 26 minus 20 will be 6. This is 18, again 18. 74 minus 20 is 54. So this times the eigenvector, let's call x1 and x2, you see? Because we are in the R2 space. So this is equal 0, 0. See? Now from here we obtain 6x1 plus 18x2 is equal 0. And 18x1 plus 54x2 is equal 0. Now it's interesting because if we divide the second equation by 3, we get the first one. So that implies that we need only one equation. So 6x1 plus 18x2 is equal 0. You can divide here by 6. This implies that x1 plus 3x2 is equal 0. You see, this we have an infinite number of solutions. Why? Because this is a homogeneous equation in which the determinant is 0. That's why you have infinite solutions. You can choose, for instance, x1 is equal 1, x2 will be, in this case, minus 1/3. You see, there are a lot of solutions. x2 is equal 3, Okay, x1 is equal 3, x2 is equal minus 1. So 3 plus 3 minus 1 is 0. There are a lot of solutions. Let's choose then for the eigenvalue here. So v1 prime is equal x1, x2 minus 3 and 1. You see, x1 is equal minus 3 and x2 is 1. Minus 3 plus 3 is equal 0. See, this is one of the solutions. But this eigenvector over here is not a unit. Okay? This is not a unit eigenvector. So I have divided by the magnitude of this vector. So the magnitude of this vector is square root of 10. So then you have minus 3 divided by square root of 10 and 1 divided by square root of 10. You observe that, you see, minus 3 is squared plus 1 is squared. This will be 9 plus 1. See, this is equal 10. You see, that's why you have to divide by the magnitude. You see, the magnitude is the square root of 10. You see, so this is eigenvectors, a unit eigenvector. Now let's do the same for lambda is equal 80. So eigenvector for lambda is equal 80. Now in this case, g minus, you see, lambda I, 80, I, this equation times vector x is equal vector 0. Now, g minus 80, okay, look, this is g, okay, g minus 80, you see, this will be equal, let's put it over here, this is g minus 80 times x1, x2 is equal 0 and 0. See? So, g minus 80i, 26 minus 80, okay? This is minus 54, 18, 18, and 74 minus 80 to be minus 6. So, let's solve. This is a homogeneous system. You see, because the right-hand side is 0, so I have minus 54x1 plus 18x2 is equal 0. And here we have 18x1 minus 6x2 is also equal 0. Now we can see here, okay, if I multiply the second equation by 3, you see, 3 times 18, let's multiply by minus 3. This is minus 54, and this is plus 18. So we can, if you want, forget one of these equations, and let's divide by 6. So 3x1, this is equal x2, you see? Divide by 6, this will be 3, and this will be, in this case, okay, minus x2. So if you take this x2 and put on the right hand side, this is x2. So we can choose, if you want, okay, v prime 2 is an eigenvector. Let's put x2 is equal 1, and let's do this. x1 is equal 1, okay? Now x2 will be 3. Now, if you divide this vector, this eigenvector, by the magnitude, if you divide by its magnitude, which is square root of 10, so we can write for lambda is equal 80. Now, this I call v prime 2. This will be 1 of square root of 10 and 3 square root of 10. You see, now we obtained the vector, the eigenvector, the matrix V, you see? So the matrix V, okay, now we have V1 minus 3 square root of 10, 1 square root of 10. Now the second column, 1 by square root of 10, and 3 divide, okay? 3 divide by square root of 10. We can see clearly, okay? Now, this is an eigenvector, this is another eigenvector. If you multiply and add, you see, that will be 0. You see? Now, we can see clearly that Vi dot Vj is equal delta Ij. So, this is an orthonormal matrix, okay? You see, this is important. Why? Because the inverse is equal to the transpose. Okay? So from here we get V transpose. We call that SVD, F, U, sigma, and V transpose. Now we already obtained F, we obtained V transpose and sigma. Sigma is the square root of the eigenvalues 20 and 80. So this 20 is 2 square root of 5 and 80 is 4 square root of 5. Now we need to obtain U. As I pointed out before, we could eliminate V to get U. But in my viewpoint, will be simpler if you do as follows. So look, let's multiply both sides by V. You see, look, F, V is equal U sigma V transpose times V. You see, let's mark V here and V here. You see? Now, V transpose times V is the identity. Then F V is equal U sigma. Now let's multiply by an inverse of sigma. You see? This is the inverse. This minus 1 over here. This will be minus 1 over here. This is F times V. Now this is I. So U is equal F V sigma minus 1. Sigma minus 1. You see, we already have F V, you see, and sigma minus 1. So from here, this implies that sigma minus 1 is equal, no, the inverse 1 to square root of 5, 0, 0, and 1, 4, square root of 5. It's very easy. Now what we need to do is to find this product, F times V, and multiply by sigma, the inverse of sigma. You see? In the diagonal, the inverse of diagonal matrix, you just calculate the inverse of the elements of the main diagonal. See? That's quite easy. Now we are ready to calculate U. So let's do it. Now the only thing we need to do is multiply matrix. That's it. So that's U. In my viewpoint, it's quicker than if you eliminate V to calculate U and the whole thing. Okay, let's calculate U. So U F V sigma minus 1, the inverse of sigma. F is 5, 5 minus 1, 7. V, see, V is minus 3 divided by square root of 10. 1 divided by square root of 10, and 1 divided by square root of 10, and 3 divided by square root of 10. And this is sigma, the inverse of this diagonal matrix is 1 divided by 2 square root of 5, 1 divided by 4 square root of 5. So you multiply and get u over here. Now, if you want to check, just multiply u, that's u, times sigma is 2 square root of 5, just sigma, you see? Sigma here is 2 square root of 5, 4 square root of 5, 0, 0. You see? You multiply u sigma and v transpose. I'm sure you're going to get 5, 5 minus 1 is 7, which is the deformation gradient. Now, we have you see, don't forget, SVD, you see, F is equal U sigma V transpose. Now, this is complete. We have F, U sigma, and V transpose. Now, we are ready to calculate the polar decomposition. So, the polar decomposition, as we did before, is Fu, just put I over here. I is V transpose V. So, UV transpose is the rotation tensor, and V sigma, V transpose, is the right stretch tensor. See? Now, F is U sigma. Now, let's put I over here. So, I is U transpose U. Now, UV transpose is R, the same R over here, see? The same R. And U sigma U transpose is T. Now, if you observe all these matrices that we need for polar decomposition, they are available here. You see, just look. You have V, V transpose, U, U transpose, and sigma. You see? And F also. You see? F, don't forget, F in the deformation gradient. You see? Now multiply matrix. So there is no problem in multiplying matrix. So in this case R, U, V transpose. So U from here, you see, and V transpose from here. So you multiply, just you get 2 square root of 5 divided by 5. Square root of 5 divided by 5 minus the square root of 5 divided by 5 plus 2 square root of 5 divided by 5. So this is a rotation matrix, rotation tensor. Now rotation tensor appears here and over there, over here. You see? Now to get S, you see S is V sigma V transpose. So you see all the matrix we need to calculate S, and also T, the matrix, they are available here. Just use it, okay? Let's get S. It's V sigma V transpose. So sigma is here, V is over here, and V transpose is over here. So let's multiply, and we will obtain 22 square root of 5 divided by 10, 6 square root of 5 divided by 10, 6 square root of 5 divided by 10, and 38 square root of 5 divided by 10. Attention, S is a symmetric matrix. See? So this is right, you see, the right stretch tensor. Now for the left stretch tensor, that's use U sigma U transpose. So here you have U sigma U transpose. So let's multiply over here. So this is U sigma U transpose. Multiply these matrices, we have the left, you see the left stretch tensor T.